Teste, teste. Alô, teste, teste, teste. Isso tem um lag. Peraí. É um lag. Teste 2. Peraí, deixa eu ver se eu teste 2. Teste 2. Teste 2. Teste 2. Então, no teste. Não, 2. Tá com lag. Pronto. Alguém quiser fazer vou desligar aqui, vai. Alguém quiser fazer
Hi, Jiajie.
Yeah, I'm here. Yeah.
Hi. Do you want to try to share your screen?
Okay, sure. Yeah, can you see my screen?
Yes, perfect.
Okay.
Let's wait a little bit. Is there any local folks? I think we can get started. It's 2 minutes past 2 p.m. Jiajie, do you want to turn on your video?
Okay, sure.
Hey. Hello, everyone. Welcome to Census Journal Track 2. So my name is Shijia, and I'm the session chair for this track. So we have in total 4 papers in this session. Each will have 15 minutes talk and 5 minutes for Q&A. So at 14 minutes, I'll try to make some noise so that you know to wrap up. So please feel free to post questions in the conference Slack channel and the YouTube chats. And for the local attendees, please feel free to step up. I think there's a mic in front of you. Step up and talk after for the questions later. So let's welcome our first presenter, Jiajie Tan. Jiajie is a graduated PhD student of the Hong Kong University of Science and Technology. He'll be conferred his PhD degree in this year. He's previously received his bachelor degree from Zhejiang University, and his research interests include wireless location sensing, Internet of Things, and mobile computing. Jiajie, please.
Okay. Thanks, Professor Pan. Hello, everyone. My name is Jiajie Tan. I'm glad to be here to represent our team to present this work, pedometer-free geomagnetic fingerprinting with casual working speed. This work is designed for classic fingerprint localization. We propose a novel speed estimation algorithm according to the data collected in a site survey, which can greatly improve the accuracy of fingerprint labeling. This work is co-authored by Han Wu and Professor Gary Chen. It is published on the recent issue of the Transactions on Sensor Network. As we all know, indoor localization is an essential and fundamental application with huge commercial value. And since we spend more than 70% of our time indoors every day, the global market of indoor localization can reach over 61,000 million US dollars by 2022. The technique enables a variety of applications, so-called LBS or location-based service, such as indoor navigation, location-based advertisement, and crowd analytics. Among different localization schemes, fingerprint localization is the most popular and applicable one in practice due to its ease to deploy, good activity, and high accuracy. It usually uses location-dependent signals such as Wi-Fi, Bluetooth, and geomagnetic field. Typically, a fingerprint localization system consists of two phases. Initially, it learns the signal distribution through a training process. This process is also known as a site survey, where a dedicated worker can walk through different locations in the venue and then collect signals there. Those collected signals, as well as their locations, form a fingerprint database, which represents the mapping between signals and locations. After that, the system is ready to provide localization services. When a user queries his location, he can sample the current signals, and then the system will search the most similar ones in the database. The location labels of the found entries indicate the current location of this user. Let's have a deep look at the site survey. Generally, there are two types of site survey. The first one is point-based. Surveyors pre-plan some survey points over the site. Then they can move to these locations, stand still there, and collect signals for a period. The second one is based on paths. Given survey paths, surveyors need to walk along those paths for several times. The signals can be collected while walking. The collecting location are estimated according to their timestamps. Generally, the path-based method is more efficient, especially when surveying some high-density signals like magnetic field. However, the survey accuracy is heavily affected by the walking speed estimation, since speed errors may disturb the accuracy of location labeling. Conventionally, such a survey assumes a constant walking speed of surveyors. We show in the right figure the impact of the speed estimation error in a site survey for geomagnetic field. This figure illustrates two sets of generated magnetic fingerprints against the location in a corridor. Since we assume the surveyor walk at a constant speed while his walking speed actually varies, the estimated location occurs huge errors. We can see the location difference of A here is around 1 meter, and the error at B will reach 2 meters. This is very significant in a site survey, especially for geometric field. Other common methods include using pedometer or supervised learning methods to estimate speed based on IMU measurement. Yet neither of them can perform well in practice. A pedometer-based method requires model assumption on stride length, which is heterogeneous to different users. The supervised scheme needs a large amount of data to train the model in advance. Meanwhile, the model is also not robust against different users. To address the speed estimation problem in a site survey, we present Mafican, an efficient and pedometer-free site survey approach for magnetic fingerprint database construction. With Mafican, surveyors can walk along survey paths at casual speed. Mafican leverages the correlation of magnetic field among different works and their IMU measurement to automatically measure the walking speed and then label signals. In that case, it does not need any explicit training in advance or rely on any model assumption. Furthermore, although our discussion is mainly on magnetic fingerprint construction, it can also be extended to other signal scenarios like Wi-Fi. Before we introduce Meficon, we'd like to discuss some important concepts in this work. For a survey path, a surveyor usually works through it for multiple times. In each work, the sampled signals, including magnetic fields and accelerations, form a sequence. A sequence can be further partitioned into multiple non-overlapped segments. We can also notice that there are two types of relations among segments: the inter-sequence and the intra-sequence. In two different sequences along the same path, we call the segment over the same physical region as inter-sequence segments, such as SEG1 and SEG2 shown in the left figure. In the right figure, we show that the two segments in different regions of the same sequence are intra-sequence segments. Given a set of signal sequences collected in the same survey path, Meficon fingerprints magnetic field by estimating working speed of each segment. It first estimates the inter-sequence speed ratio. Since similar magnetic fields can be captured when passing the same region, Meficon uses sequence alignment technique to identify the location correspondence among different sequences. In particular, we employ an efficient hierarchical method based on DTW to align multiple sequences. By comparing the duration of the aligned segments, their speed ratio can be obtained. Next, Meficon estimates the speed ratio of intra-sequence segments. To achieve this, we employ an SVR model to capture the correlation between accelerations and the speed ratios. And the model is self-trained by using the aligned inter-sequence segments according to the previous step. After training, it can predict the speed ratio of any intra-sequence segment pair. Finally, with both inter and the intra-sequence speed ratio, Meficon derives the absolute speed by formulating a quadratic programming. In the following, I'd like to show the details of Meficon. Meficon first estimates the speed ratio of inter-sequence segments. This is estimated by alignment, which identifies the corresponding working region in different sequences. Typically, alignment in two sequences can be obtained by applying DTW. It uses dynamic programming to compute the optimal matching between two sequences. Besides, since magnetic measurements on device is under device uncoordinating system, it is hard to compare among different sequences. In our implementation, we transform the magnetic field samples into the orientation invariant but location-dependent features, including its magnitude, horizontal component, and the vertical component. In practice, surveyors usually walk the same path multiple times. To obtain the alignment among multiple sequences, we first apply a hierarchical multi-sequence alignment. The alignment uses an iterative way. In each iteration, we merge the two sequences with the lowest DTW distance. This repeats until only one remains. Thus, we can obtain the alignment over all the sequences. Meanwhile, the overall alignment also provides a reasonable way to partition sequences without any conflict. We partition the remaining sequences with equal time interval, and then segment the others following the alignment. Since any pair of aligned inter-sequence segments represents the same working distance, we can simply estimate their working speed ratio as the inverse ratio of their time cost. Inter-sequence speed ratio alone only reflects the relative speed and cannot provide the actual speed. To address this, we estimate the intra-sequence speed ratio. Considering that user mobility directly affects walking speed, we employ a self-learning scheme. That is, we use the inter-sequence segments as the training data set. In that case, we don't need to gather any training data beforehand. The model can be used to predict the speed ratio of any intra-sequence segment. We extract features from the acceleration readings of each segment in both time and frequency domains. To combine the features in segment pairs, we perform subtraction and division to link them. In our system, we recommend SVR because of its strong learning capacity and less data requirements. Finally, based on the estimated speed ratio, we formulate a quadratic program to estimate the speed of each segment. Our objective is to find the speed to minimize the inter and intra-sequence errors. The constraints are that the total walking distance should equal to the path length and each walking speed is greater than 0. By solving this, we can label the precise location to collected signal. To validate Meficon, we conduct extensive experiments in different types of scenario, including a corridor, a mixed area, and an open area. In each scenario, we plan survey paths and invite users to walk along those paths for 6 times, just similar to their normal survey process. They can walk at their own speed and change their speed at any time. We evaluate the system performance in terms of walking velocity error and magnetic fingerprint error. To obtain the ground truth during walking, we use a camera to capture a simultaneous video and compare with distance labels on the ground to record the user's actual walking speed. Meanwhile, we also take a point-based site survey every 0.2 meters as the ground truth fingerprint. We compare Meficon with 3 existing schemes, which are assuming constant speed using a pedometer and using a supervised learning method to estimate walking speed. We first compare the accuracy of speed estimation among different methods. We can clearly see that in all the scenarios, Meficon achieves the lowest error, which cuts the error by 20 to 30%. This is because Meficon not only leverages the acceleration features as the other one does, but also uses the correlation of different sequences to improve the estimation performance. In this slide, we show the accuracy of generated fingerprints. Benefit from the good performance of speed estimation, Meficon also outperforms all the other schemes. The errors are lower than the others by 30 to 40% in terms of the magnetic fingerprint error. We also evaluate the fingerprint errors and the different users and devices. The upper figure shows the fingerprint error of different surveyors using the same device, while the lower one plots the fingerprint error when the same surveyor uses different devices. We can see that in both cases, our algorithm has stable performance against heterogeneity, which validates the adaptivity and the robustness of Meficon. Localization is the ultimate goal of Meficon. We further conduct experiments to evaluate localization performance on the constructed fingerprint database. In particular, we implement a classic magnetic localization system named Magical. The bar chart demonstrates the localization error under the fingerprint generated by different methods. Among all the schemes, the localization performance of Meficon is the most stable and the closest to the ground truth database. Finally, let's conclude this presentation. In this presentation, we introduce Meficon, an efficient site survey method based on speed estimation. By using Meficon, surveyors can walk along the survey path at casual speed. Meficon leverages the correspondence of magnetic fields to estimate inter-sequence speed ratio. It also applies self-supervised learning to estimate intra-sequence speed ratio based on acceleration measurement. Based on above, it uses a quadratic programming to estimate the surveyor's actual walking speed and then label signals. We also conduct extensive experiments in multiple sites and validate the performance of Maficon. Thank you.
Thank you very much, Jiajie. Any question from the local audience? So I do have a couple of questions. So I noticed that you guys tested had the experiment that along the one hallway that you have 3 or multiple different paths, like has
Yes.
relative location. So I'm wondering whether you can comment on how sensitive is the fingerprint over different passes, and how sensitive is your method, say, to this changes in the fingerprint variance over different position along the hallway. For example, you test 3, is that sufficient? What happens if I work at 5 different locations? Would this tiny change impact your system, your fingerprinting performance?
Okay. Firstly, if it is a hallway, then the pre-planned path, it only has one pre-planned path. So every surveyor or one surveyor will work this survey path for multiple times. And for another example in our experiment is an open area, and there will be several parallel survey paths along cross this open area, and those survey paths will cover the whole area. And secondly is that in our experiment, if for magnetic field fingerprint localization system, then usually the granularity is 0.1 or 0.2 meters. And in this range, and the magnetic field will have a significant difference. So when we evaluate this system, we conduct another point-based site survey every 0.2 meters, and this is sufficient to evaluate the system performance.
I see. That sounds really great. So how about the dynamics in the environment? Say if you have one survey or multiple survey, but the ambient environment actually changes, which potentially would also change your fingerprint, may or may not. So how, like, temporal-wise, what's your comment or solution to get high accuracy?
That's a very interesting question. Yeah. So in our system, we only address the problem of site survey. So it means the site survey usually occurs in a short time, like 1 day or several hours. So we assume that in this period, the environment does not change. In other case, if it is in a large time scale, like 1 month or 2 months, and the environment may change, then one way is to redo the whole site survey, and the other way is to use some updating method like the crowdsourcing to update the fingerprint. But that's it. That's the out of the scope of our work.
I see. Any local questions? Oh, there's a comment. There's a question on the YouTube channel. So from Ada, thanks for the talk. Any intuition on why the arrow across corridor is larger overall compared to other passes?
Sorry, can you say that again?
So it's any intuition on why the arrow across corridors is larger overall compared to other passes.
Oh, okay, yeah. Because the dynamic of magnetic field is usually introduced by the some magnetic or metal materials. So usually along the corridor there are more structures, so it will influence magnetic a bit. But when it is when you are in the open area, and the whole trend of the magnetic field will trend to be very plain. So the variance of magnetic field alone will not significant. So the error will be less.
Thank you so much for the answer. It's a really interesting work, and it's very important to have the technology to be robust and easy to use. So thank you.
Thank you.
I think we can move on to our next talk. Is Suzhe here? I think we are missing our second speaker, but our third speaker, Bo, is here. Bo, do you want to continue your talk then?
Yeah, I don't mind. Yeah, I don't mind. If you want.
Thank you.
Yeah, just change another camera. It's scary to use this one. Yeah. Okay, so let me share my screen. So can you see my screen? Should be a mountain right now.
Yes. See, yes, now we can see the slides. Great.
Do you want me to start now? Or
Yes, I think we can get started. So welcome our now second speaker, Dr. Bo Wei. Bo is a senior lecturer at Northumbria University in the UK. He was a postdoc at the University of Oxford and obtained his PhD from UNSW, Australia. He was also a research student in CSIRO, Australia, and visited the SICS in Sweden as a visiting research student. So welcome, Bo.
Okay, thank you. Thank you for the introduction. Hello, everyone. This is Bo from Northumbria University in the UK. The first author of the paper named No Need of Data Preprocessing, a general framework for radio-based device-free context awareness, which is accepted by ACM transactions on Internet of Things. This paper is a collaborative research work with researchers from China, Portugal, and the US. Please allow me to use this opportunity to thank all the co-authors for the contribution. Here is the outline of this presentation. So let's start from the introduction. Radio-based device-free context awareness is a popular area in the wireless networking and sensing research community. So it has a wide range of applications, such as localization, activity recognition, identity recognition, and sign language recognition. So I'll give a little bit more background about the radio signal we use. We use channel state information, or CSI in short, for this research. Compared with the traditionally used radio signal strength, it is more informative with 52 or 30 dimensions, depending on which hardware you use. While the radio signal strength can only provide measurements in one dimension. With more information, so less devices are required. So usually a pair of radio devices is needed. But of course, this depends on coverage areas. When using radio signal strength, it usually uses multiple devices around the places of interest for resolution. So where does this CSI come from then? So Wi-Fi physical layer uses a multi-carrier modulation method called orthogonal frequency division multiplexing, or more commonly OFDM, which provides a complex valued CSI for each subcarrier. So due to a random phase shift in OFDM from the unsynchronized time between the transmitter and the receiver, it is challenging to directly use the phase information without explicitly processing in context awareness applications. So the context awareness using radio signal usually belongs to supervised machine learning problems. So that is to match the measurement to be classified in a dictionary for a prediction. Traditionally, signal processing is firstly used to obtain amplitude and or phase information in a unified dimension. So we can see that step as feature selection, and then use supervised machine learning methods as classifiers. But when looking at the other domains, such as computer vision, traditional handcrafted feature selections are not often used now. And instead, deep learning is applied on raw data directly for prediction. So our research is actually motivated by this. You may ask, the question that is signal processing, for example, obtain amplitude and phase is widely used. Why do we still need a new framework or new method? The use of amplitude of CSI is very common, as it is more consistent compared with using phase. So which is good for the use of supervised machine learning. However, complicated situations need more information, such as noisy environments with more radio interference and numerous classes. So the addition of phase can definitely bring more information, which can definitely help enhance the recognition performance. However, one disadvantage is that it brings more inconsistency due to the use of an artificial threshold. So let me give you more details about the inconsistency. As I mentioned, a random phase shift exists in OFDM due to unsynchronized time between the transmitter and the receiver. So a process was proposed to try to make them consistent. So we won't go for details here, but one important step is to unwrap is to arrive the phase if the changes of the neighboring subcarriers are beyond a threshold. The default threshold is pi or 180 degree. Just imagine these phases are in the complex domain. It is very common that its neighbors go across the axis, which makes a big difference. But actually, the difference is not that big in the complex domain. So unwrap is used at that time. Again, if the changes are beyond 180 degrees, the phases of the following subcarriers are unwrapped. But always there are a percentage of samples that the difference is just around the threshold, which makes samples not consistent. Again, those samples are supposed to be consistent for supervised machine learning. For example, the raw phases of the second sample and the third sample are very similar before unwrapping, but after unwrapping, they look very different. This is not good for supervised machine learning method. Please note the inconsistency is actually from the involvement of signal processing. So therefore, we were thinking that we could remove this step and use raw CSI data with amplitude and phase information directly without any pre-processing. So this is actually very challenging because the phase information from measurements is actually very different, like I mentioned. So we solve this by proposing a novel deep learning-based framework. So after showing the introduction and the motivation, here I list the contributions of my paper. To the best of our knowledge, this paper is the first to propose a novel deep learning-based framework using raw CSI data for context awareness without any feature selection and initial data pre-processing. And we show the intuition and theoretical explanations in detail in the paper for the application of the raw CSI on training the DNN model. We conduct extensive evaluations on various data sets to demonstrate the generalization of our framework. Here we use one figure to show the difference between our proposed model and the traditional model. We remove the signal processing stage and take full advantage of deep learning techniques for radio-based context awareness. So that is the main contribution of our paper. Here are the details of our proposed framework. The input is the complex valued CSI. The deep learning, the deep neural network starts from a convolutional layer, then follow with multiple convolutional layers and the batch normalization layers. The next part includes average pooling layers before passing it to a concatenate layer, which is here. The next part is multiple fully connected layer and drop-off layers. And the final layer is a soft mask layer for recognition. So we use two data sets from these two papers in our evaluations. The first one is sci-fi with 276 classes. This dataset has far more classes than the other datasets. And the other one, the other dataset is called the activity dataset, which collected data in two environments. So that is from a clean environment, as well as and the radio interference, which brings more challenges. Due to the limited time, we only show the performance of our proposed method in activity dataset. So you can find more results regarding the sci-fi, the performance on sci-fi dataset in our paper. Here I give some quick dataset description. Like I mentioned, CSI samples in activity dataset has been collected in two environments. We call them AD1, which is clean environment, and AD2, which is under radio frequency interference. So in each environment, we have 8 normal activities. And for each activity, we collected measurements for 10 minutes using a sampling rate 1 Hertz. Here is the architecture of the DNN model for activity dataset, which includes 7 convolutional layers, 3 average pools, and 2 fully connected layers with different settings. So let's have a look at the performances of this DNN model. The first performance is comparison with sparse representation classification method with feature selection. So in AD1, clean environment, the to propose the method outcomes SRC, and in AD2 with radio interference, they achieve equivalent performances. Here, SRC stands for sparse representation classification method. But please be noted here, the proposed method actually does not use any feature selection or signal processing. But when using the SRC, the feature selection, also called signal processing, was used. So we're looking at the performance with respect of the number of convolutional layers. It is clearly seen that the increasing number brings higher true detection rates. And these two figures shows the effect of batch normalization layers, which can significantly increase the performance. So we're looking at the effect of the average pooling layer. It also can increase the performance in AD2 under radio interference. So we also show the effect of deep learning by comparing it with a classic random forest, which can clearly show the advantages of the use of deep learning. Okay, so just to conclude, we proposed a novel DNN-based framework for radio-based device-free context awareness without any data pre-processing. We also use the public radio-based gesture recognition datasets and the activity recognition datasets to evaluate our proposed model, which results in very good performances. So that is all I want to discuss with you. Please have a look at our paper for more details. I also leave my email address here. So if you have any questions, please feel free to drop me an email. So any questions now? Thank you.
Any questions from the local audience? While I think the YouTube has a delay, so let's wait some more time for them to type in the question. But meanwhile, I do wonder whether you can comment on, say, with just a raw data versus extracted feature, what are the trade-off between, say, explainability and the amount of data that's needed to acquire robust or high accuracy?
Yeah.
Yeah.
Yeah, that's a very good question. So like I mentioned, if the situation is very simple, so we can simply use the amplitude or phase. But we have a lot of more complicated situations. Just like the two data sets I used for the first one, it has more classes, more than 200 classes. So if we do not use both amplitude and the phase information, so we may not have enough the data or enough information to get a very good performance. The same for the second data set, which has the noise or radio interference. If we do not have the phase information, so probably we cannot achieve that good performance. So that's why we hope to use both amplitude and phase information. But you're right. So in that case, there are two choices. The first one is to involve signal processing, but sometimes it's just give us some wrong, the prediction results due to the involvement of artificial thresholds. So in that case, we have to think to use the raw data. So that's kind of like the idea in computer vision. We use the raw images and we can get all the data. We won't lose any information due to the data processing. Yeah. So that's the idea in when to use our method, when to use our framework. So I hope it answers your question.
Yes, that's really great. So we have a question from the Slack channel. So from Barazan. So thanks for the nice presentation. Can you describe the raw data input to the deep learning model again? I saw 1 Hertz signal for 10 seconds. Is that a single receiver measuring CSI or multiple? Do you do any feature transformation, for example, normalization or smoothing?
Yeah. So I think they asked some description about this one. So for this one I just use the raw data directly. So some normalization could be used before, but it's not necessary. Yeah. So I hope it answers the question. So so for this one, I think I forgot to mention. So what I did is basically to collect the data, and then you are right. If we do not do the normalization, the amplitude, or we can call that the power of the collected measurements are not equal. After normalization, they look more alike or more similar. So, but when using the deep learning, so we could do normalization, or I tried if we do not do normalization, the performance are basically very similar.
Thank you very much for the answers. So due to time limits, we're going to move on to our next speaker. Thank you very much, Bo.
Thank you. Thank you.
So our next speaker, Sijie An. Sijie, are you ready to share your slides?
Yeah, I will share now.
Great. So Sijie is a 4th-year PhD student at the School of Electrical and Computer Engineering at the University of Wisconsin-Madison. His current research interests include human activity recognition, 3D human pose estimation, meta or few shot learning, and algorithm design for smart healthcare. Please go ahead, Sijia.
Thank you, Professor Pant, for introducing me. And yeah, hello everyone. My name is Sijia, a PhD student at UW Medicine, and today I'm going to present our paper MGATE, model-based gait analysis using wearable band and inertial sensors. Yeah, so the risk of amputation, for example, losing an arm or leg, has increased sevenfold for patients all over the world during the COVID era. But what causes this enormous increase? The fact is that the patient's access to healthcare has decreased during the pandemic. A significantly lower number of patients with symptoms of fundamental disease and movement disorders sought help compared to the pre-COVID time. So this result implies that a home-based health monitoring system is needed. Evaluation of gait metrics is the first step towards the rehabilitation of movement disorders. Rehabilitation is extremely important in helping patients regain their quality of life. So gait metrics, including step, stride length, and velocity, reveals to what extent the patient rehabilitates. But however, as mentioned as before, patients' access are limited to the healthcare resources, especially during the pandemic era. So we can see that there is a strong need to develop a home-based gait monitoring system. So currently there are some solutions. The most accurate one is GaitRight, a matrix with more than 20,000 sensors. It is extremely expensive, which is not practical for having it at home. And there are some accelerometer-based approaches. Usually the resolution are not to each step and not very accurate. There are also some video-based approaches, which requires strict environmental setting and for example, like light condition and raise some privacy concerns. So to address all these concerns, we propose MGATE. It is explainable since we have a closed form formulas for the gait cycle, and then we achieve low power and low cost using the inertial and bendable sensors. So MGATE provides multiple metrics, including step, stride, length, and velocity. It also provides the valuable insights for the rehabilitation process. So using these metrics, MGATE offers users also feedback such as the gait asymmetry detection. So here we give an overview of the MGATE flow. So we use the band and inertial sensors to compute the hip and knee angle. So which you can see here, the hip and knee angle. So we decompose a total gait cycle for 4 stages: the initial contact and opposite foot off, opposite foot strike, and foot off. Then the new initial contact start again. So first, we find the minimum of the front knee angle, as we can see the point A in the plot. And we can also find the hip angle of the same leg at the same timestamp. So these 2 angles are all we need for the front limb. So then we find the minima of the back hip angle. So after the previous timestamp, which is the point D, this one. So at the same timestamp, we can also find the knee angle of the back leg. So these 2 angles, C and D, are all we need for the back limb. Then using these 4 angles together, the A, B, and CD, we can compute the step length of one step based on our model, which I will introduce in the next slide. So after that, the front limb and back limb take turns, and we can compute like this for every step, every single step. So this is an overview of the gait model that we developed. So we have L1, which is the length of the thigh, and L2, which is the length of the leg. So depending on where the back limbs are, there will be 2 different cases. So we can let's focus on the left one first. where the alpha B is negative. So we decompose one complete step into 5 different portions, D1 to D5. So D1 is the projection of the front leg on the ground. And D2 is the projection of the front side to the ground. And D3 is the projection of the back side to the ground. And D4 is the projection of the back leg to the ground. And D5 is given by the diameter of the subject side below the gluteus. So now the beauty of this closed form solution is that if you look at the other case, the right one, when the alpha B, the alpha back, becomes positive, the D3 will actually become the negative one, as we're showing here. So and the closed form solution still holds for the right scenario. So I'm saying that these two scenarios can be combined into one formula. So let's take a look. This right case, so it will become D1 plus D2 plus D5 plus D4, and then subtract the value of the intersection of D5 and D4, which is D3. So this model accurately reviews the nature of gait and parameterize it using the hip angles and the knee angles. So here I'll introduce the sensing part. We use a band sensor from the Band Lab, a commercial bending sensor, and also a commercial IMU, inertial sensor, for getting the both hip and knee angle. So for hip angle, we use the IMU sensor, which contains 3 axes accelerometers value and 3 axes angular velocity values. So using these values, we can compute the hip angle. I'll introduce the methodology later. And for the knee angle, we use the band sensor, which can accurately measure the angle between 2 edges. So we apply a downsampling and smoothing filter to reduce the noise in the data, as shown in the formula. So the specifications of the sensors before and after filtering are shown in the table. So we use accelerations and angular velocity to compute the pose angle of the IMU. Specifically, we use the Magic filter to fuse 2 kinds of data. So the Magic filter uses the quaternion representation of the accelerometer values and applies a gradient descent algorithm to calculate the error in the direction of the gyroscope samples, which is the angular velocity. So by compensating for the error, it accurately estimates the orientation of the IMU even during the motion without being affected by the gyroscopic drift. So as we can see in the figures, Magic filter takes the accelerometer and gyroscope data showing in figure A and figure B, and then outputs the smoothed hip angles as shown in figure C. So for the math derived, please refer to the original paper of the Magic filter. So sample knee angle data from our experiment is visualized in the figure A. A comparison between the raw and filtered data shows that the averaging filter smooths out the variations in the data. And the knee angles reached a maximum of about 50 to 55 degree as the leg swings. And another key observation is that the angles of 2 legs exhibit approximately 50% phase shift when walking. So this is expected for healthy subjects since their steps are of the similar length. And figure B plots left and right hip angles during walking. The hip angles vary between a maximum of about, a minimum of about minus 10 degree and to a maximum about 35 degree, and exhibit 50% phase difference as expected. So in this slide, we'll talk about the offline and online estimation of static parameters. So we have 3 kinds of static parameters, which is L1, L2, and D5, the length of the thigh, the length of the leg, and hip diameter. So since measuring them is subject to human error, so we employ both offline batch processing and online least squares regression models to determine these parameters. So batch processing is a common method used in least square estimation. So for our step length estimation problem, batch processing is an effective solution when the gait analysis is performed offline. For instance, a patient can walk for a few minutes while measuring the ground truth length reference, and then the collected data can be used to do the least square estimation, and then to find out the error, to reduce the measurement error by tuning the model. So we have this objective function to minimize and subject to the realistic range of the static parameters. So here is the 90% to 110%. It is also useful to fine-tune the model in real time after it is deployed, since it can help the proposed system to adapt to a particular person. So batch processing is not appropriate for this purpose, as it requires the offline processing. So therefore, we also introduce a recursive least square estimation framework that can calibrate the static parameters for a given user. So when the step length model needs to be updated, for example, for a new user, the system operates in a calibration mode. And in this mode, the user is asked to walk in a line with a constant step length. So during this time, the RLS filter estimates the step length as a product of the HN and W, so which are given here. Then this estimate is subtracted from the reference step to find the modeling error. So this error is then used to update the parameter estimates W, this static parameters, using the RLS technique with stability guarantees. So the implementation details of RLS is shown in the reference. And we also have the formula in our paper too. This is the specific implementation. So here we analyze the angle. So the angle measurements are also subject to error, the human measuring error, due to the noise nature of the sensors. So furthermore, sensors may experience a systematic bias due to their positioning. So this difference should be accounted for in the models to ensure an accurate estimation of the step length. So to compensate these errors, we solved the nonlinear regression problem given in the previous objective function again by using the static parameters found in the batch LS. So this time we'll try to find the angle as the variables. The output of the nonlinear regression gives the average knee and hip angle that provided the minimum estimation error. So hence we use the difference between these values and then we do the shift our observations as the measurement bias. So this slide shows some of the quantitative results of MGate. So here the step length is the length of one step, and adding two consecutive steps together, we can obtain the stride length as well. Using this length and the time, we can further compute the velocities. So the average mean absolute percentage error in step length estimates is about 10% when we use user measurements without any error correction, as we can see in the initial legend in the upper plot. The error is reduced to about 7.2 with batch LS. We can see in the red legend, the fit 1. And then the error further reduced to 5.4% when we remove the angular offset in the angle measurements. So we can see the white and blue legends here, the fit 2. So in particular, the mean absolute percentage error for subject 2 and 5 drops by more than 10% since they have a higher initial error due to the inaccurate limb measurements. So the table shows specifically after fit 2, the metrics for each of the users. So this result shows that the proposed model is able to accurately estimate the gate parameters. So in this slide, we will introduce the gate asymmetric detection. So patients with movement disorders often have different left and right step lengths. Therefore, we include gate asymmetry as one of our feedbacks that we provide to the user. Our metric, the percentage gate asymmetric, quantifies the difference between the left and right steps length in the same stride. So if the difference exceeds the threshold, we then identify there is an asymmetric stride, and we notify the user of gate asymmetry using a buzzer on our device. So as shown in the figure, this figure, the subject starts walking, aiming for walking with symmetric steps in strides. And then after 78 strides, which is here, the subject starts making one regular step, following by one short step, which is the gate asymmetric. So we can see that mGate keeps track of the percentage gate asymmetric in a stride and successfully detects the gate asymmetric after the 78 step. So low power operation is crucial for mGate to offer a long-term gate monitoring solution. To explore the power consumption of mGate, we measure the actual current consumption of the bending sensors and IMUs. So connected to a 150 milliamps per hour battery, the bending sensor can run more than 12 days in idle mode and 65 hours in the sensing mode. Similarly, the IMU can run more than 12 days in the idle mode and 43 hours in the sensing mode. So this result shows that mGate offers a promising low power solution for long-term gate monitoring. We also propose a technique that generates the synthetic data. For the interest of time, I will not go into details. The idea is that we train a convolution, the conditional generative adversarial networks, the CGAN, for the synthetic data generation. I'll skip the details here. So in conclusion, the novel model design of mGate successfully built bridge between human gate to closed form solution. And mGate is one of the first steps towards the practical home-based health monitoring system. And it provides users with valuable metrics and feedback and can be operated for long-term usage due to the low cost and low power solution. So the dataset is open source and will be updated in the following GitHub page. And my email is here. Please contact me if there's any problems. Thank you very much. I'll be happy to answer any questions you might have.
Thank you very much for the great talk. Any questions from local audience? And please feel free to type in your questions in the Slack channel or the YouTube chat. Meanwhile, I will start with some questions. For example, I think what you are measuring, the angle, is at a particular gate cycle. I don't know which one it is, but I'm one, and you have a model talking about the relation between different angles. And I'm wondering whether for a particular disease, this model might change, or this cycle might be very different from the like a healthy walker. So can you comment on that, please?
Yes. So you're right. We are measuring the angle for like specific time stamps inside of one gate. But actually, we measure like the whole gate, but we just choose specific timestamp to get these angles to compute. And so this is of course for the healthy subject, but we assume that this also holds for patients, because as you can see, each component here are very clear for the gate. But we didn't evaluate this on actual patients due to the IRB protocol and those complications, but we absolutely want to evaluate this on patients also.
Thank you for the answer. So is it possible that for some patients, the A, B will never be in the situation that describing B, for example? If that happens, how would your system handles it?
Yeah, so I think for alpha B, we considered both situations. For example, it is leaning forward, and for example, it is leaning back. But your answer could your question could be right for the alpha F, because we only considered leaning forward here. Yeah, if the patient like for example have a limb that can never going forward, then yeah, this formula doesn't support that case.
I see. Thank you very much for the answers. So due to time limits, we'll move on to our last speaker. Thank you again, Sijie. If
thank you.
there are more questions for Sijie, please. Actually, there's a question in the YouTube channel. I'll post that in the Slack channel, and you probably can answer it there from Ada. Yeah.
Thank you.
And we'll move on to our last speaker, Dr. Atis Estes, who will present from the local. So Dr. Atis is a postdoctoral researcher at the Institute of Electronics and Computer Science, EDI, Riga, Latvia, and an honorary senior research associate at the University of Bristol, UK. His interests include Internet of Things systems and protocols, which focus on low-power wireless networks. Dr. Atis, please go ahead. Hello? So, session manager, could you please check the audio from the local site?
At the University of Bristol. So in the SPHERE project in Bristol, we look at monitoring people's health inside their homes. To this end, we aim to collect data from multiple sensors and to deploy the sensor collection system in more than 100 homes. The goals of this deployment are multiple. First is to validate the sensor platform itself. Then it is to collect a data set from healthy people for control. Then finally use it for clinical applications such as recovery after surgery or chronic health conditions such as mental health, diabetes, and so on. There are three main sensing modalities in the SPHERE platform: environmental sensors, wearable, and video sensors. The first two of these form the low-power wireless network, together with the gateways and forwarding nodes, which form the infrastructure of this network. I'm going to talk briefly about the hardware now. So the SPHERE wearable samples accelerometer with sampling rate of 25 Hz per second. And we aim to deploy one device per person, and can be up to 5 persons per household. And this is based on the Texas Instruments CC2650 system on chip, same as the other hardware. The environmental sensors samples temperature, humidity, and light levels. And we aim to deploy one device per room. And finally, the Sphere Gateway hardware is used for data collection and forwarding, and it also samples the signal strength from the variable in order to localize people inside the room. This is based on the same chip, but we have 2 radios per device, so we can use to bridge multiple networks with this. And there will be multiple devices per house. So putting it together, the architecture of the network looks like this. We have environmental sensors sending data to the forwarding gateways. We have the forwarding gateways forming a mesh network and then sending data to the main gateway, which is connected to the data storage server. And we also have the variables sending data to the forwarding gateways, and the gateways also record the signal strength. So we considered multiple protocol options for the system. We put away some as not useful, and we stuck with Bluetooth Low Energy and the TISH or 6LoWPAN. So we selected Bluetooth Low Energy for the variable to gateway part of the network because Bluetooth Low Energy has good support for mobility, and TISH for the rest of the system. To briefly talk about the TISH protocol, it has some nice properties suitable for the application. So this is a protocol standardized by IEEE in 2016. The properties that we want is high reliability in combination with low energy usage. And it's also resilient to interference, mostly because of the channel hopping. So the way a TISH network works is that there's a single node called coordinator, which creates the network, and other nodes join. The coordinator counts time from 0 to basically infinity. All the time is divided in time slots, and the communication only takes place in a specific place in the time slot. Time slots are grouped in a slot frame, and in the slot frame we have 2 dimensions. One is the time, the second is the channel or the frequency dimension. And this channel offset is mapped to the physical radio channel by using a network-wide hopping sequence. And the way it works is that even cells with the same channel offset typically get a different physical channel in the next time slot. So when we retransmit a packet, this packet is likely to be retransmitted on a different channel, meaning that a single bad channel will not break down the whole system. And there are also idle slots which can be used to sleep. So this is obviously promising for the application, but there are some challenges with state-of-the-art. One is that the scheduling is not standardized by IEEE. There are, of course, other schedules that exist, but typically TISH is used for industrial applications. And typically these schedules are for quite low data rate networks with homogeneous single application use cases. And TISH is definitely not investigated experimentally in the target area of smart home applications, which like in Sphere, we have some specifics, like we have quite high data rates because of the variables produce a lot of data. And then we have multiple classes of devices in a single network. We have the gateways and forwarders, which need reliable high packet rate network. And then we have the environmental sensors, which want to have as low duty cycle as possible because they're powered from the battery. Finally, the data rates is also quite highly dynamic. I'm going to show what I mean by that. So in the left side, you see network deployed in a house. We have a number of gateways, we have a number of environmental sensors, and we have 2 variables distributed around the house, which send data to some of the forwarding gateways. But people don't always behave like that. Sometimes people congregate in a single room. Let's say we have a family of 5, and maybe they're all watching TV. And in this case, the single gateway in the living room would handle all of the data. And this situation might actually happen very suddenly. Let's say that all of the people enter the house at the same time. Then the data rate requirements go from basically 0 to the maximum on this gateway in the whole So to solve these challenges, we propose a new adaptation layer, which sits between the standard IEEE TISH protocol and the network and application layers. This TISH has three distinct features. First is adaptive channel selection, the third is new schedule, and the third is load balancing mechanism by multiple gateways. So to jump into the way that TISH schedule is constructed, we have let's say a network like this. We have multiple forwarder nodes and a single main gateway node and one environmental sensor. Then we sort of construct the basis of the schedule at the compile time. We put it in the firmware of the device. So we reserve some cells for the forwarder to main gateway communication. But then we also reserve cells for all of the possible combinations between the other gateways. So we have n times n table in the firmware because we cannot guess what the topology of the network is going to look like in the runtime. Then we also have a single shared slot in this block, which is used for the sort of the overflow handling when the gateway has too much data sent in this normal part. And then at the runtime, we activate some of these cells. Obviously, we cannot activate all of them because a single node is only capable of sending single packet at a single time instant. So we don't need to do any communication for this whatsoever because we rely on the routing information. And when we use the RPL routing protocol, by default, it only has single parent, so we only need to activate single cell to send data to this parent node. But for the shared slot, there's a different approach. So this shared slot is activated based on the requests from the forwarding gateways to the main gateway. They can request extra slot, and on the first come first served basis, this is reserved for one of them, just for this single specific instance. And then putting this together, we have the whole sphere slot frame. We repeat the block that I described multiple times in the slot frame. And the slot frame has actually three different components. The first is the common part, which is used for network management traffic with a single slot. Then we have the repeating part of the blocks for forwarder to gateway communication. And then we have a single block for environmental sensors. So a single environmental sensor gets only a single slot in that block, and total it gets 2 slots per second per slot frame, which is very efficient, while the forwarder gateways get many slots per each slot frame, which let them to handle high data rates. But even that is not sufficient for the application, because theoretically there can be more than 100 packets per second in some cases. And this is not possible with the standard TISH, which has only physical capacity for 100 slots. There are also some other problems. For example, it's a single point of failure of the single root node, and we don't use the spatial diversity in any way. So what we propose is the multiple gateway approach, that we also have a secondary gateway. We look at 2 different ways how to get integrated in the system. The first is sort of what we call layer 3 load balancing, sort of the typical what you have in Linux-based systems, that you have a route, then you have multiple next hops for the route, and then when you have a packet, you select one of these next hops and you keep retransmitting the packet to the same next hop again and again. The problem is this approach, that if we have bad link to one of these, so the main gateway or the secondary gateway, then we keep retransmitting the packet again on a bad link. So we propose also this layer 2 load balancing. When we transmit on the first link, then next retransmission will happen on the next link, and so on. And we show in the paper that it's behaving much better. And of course, we can use this approach also to actually load balance, meaning because we have multiple channels in the system, we can transmit packets at the same time without interference by transmitting them on the different channels. from different devices. And on the left-hand side, you have the first transmission attempt, then on the right-hand side, you have the second attempt, which uses different links and also different channels. So to evaluate this approach, we compare with the state-of-the-art schedules in the test house. We selected Orchestra and 60 MSF for the comparison. Orchestra because it's widely used and widely cited. Orchestra also allocates cells autonomously, so without management traffic, but it only has one active cell per slot frame per link. So unlike our schedule. And then the 60 schedule, which is just recently standardized, it has distributed components that we kind of talk between neighbors to agree how many cells do we want. And this is quite slow in practice. So it's slow to react to changes. So this is the main evaluation result that I'm going to show in the presentation. So on the top, you see on the top left, you see the sphere dish performance. As you see, in experiment, we increase the packet rate from 10 packets per second to up to 60 packets per second, and we still get perfect reliability. We also get the same actually with Orchestra, with this short slot frame Orchestra. But the issue is when you look at the right side, that you see how many active slots per second we have. And with the shortest slot frame Orchestra, we have about 8 times as many slots as with the sphere. And if we make the comparison fair by using a longer slot frame Orchestra, then we see that actually the performance in PDR is quite bad. But the MSF was also bad. And even for the 10 packet per second case, it was not able to react fast enough to establish the schedule, while clearly the network had the capacity to deliver more than 60 packets per second. So it was not suitable for the application. Finally, we deploy and validate the system in real life. Sort of we have homes in Bristol, and we analyzed 29 deployment results in the paper. We measured packet delivery rate, energy consumption, and other metrics. And the main takeaway, I guess, is that we have good results from the deployments, but we had much better results in the sphere test house when we fine-tuned the system for the specific house. So in the test house, we sent 15 million packets. We received all of them, 100% PDR, basically. In the real life houses, we have varied results. So in a single gateway case, we have 99.8% PDR, and in 2 gateway case, we have the 99.96% PDR. But as you see, also the houses are quite different in terms of performance. To summarize the presentation, we are first, as far as I know, to investigate the TISH protocol for the residential health smart home IoT applications. We identify the strengths and the challenges of the protocol in this application, and we propose the sphere TISH adaptation layer, which has novel TISH schedule, a load balancing mechanism, and adaptive channel selection mechanism, which I'm not talking about in the presentation because of the time limits, but which is described in the paper. And we evaluated in a test house and in 29 real life houses. We show that the performance is better than existing schedules that can deliver up to 112 packets per second with perfect PDR in the sphere test house, and that has 99.96% average PDR in the real life houses. So before the questions, I want to thank all of the sphere researchers and technicians, more than 50 people who worked on developing and deploying the platform and who made this research also possible. Thank you, and thank you, the audience.
Can the audience comes up to the mic?
Maybe I can repeat the question.
Yes, please.
First of all, thanks for the presentation. It's always nice to see these empirically validated deployments. I was wondering, you mentioned that you might consider multiple technologies or Wi-Fi for this kind of application context. I was wondering whether you also have considered like these synchronous transmission protocols seen emerge over the past decades, because it seems like these might help you with mobility or high communication. You might have on efficient deployments.
Sorry, you mean asynchronous or synchronous?
Synchronous transmission, like these protocols like
Glossy, yeah. Okay, so the question was about whether I'm also considering synchronous transmission protocols like Glossy for the application. And yeah, it's sort of tempting to try to deploy something like Glossy. Obviously, I know the work and I like it. One thing we had, you mentioned, you saw that I mentioned multiple standards, so we want to sort of be standard compatible. And as far as I know, there are no standards related to the synchronous transmission protocols. So for these real life deployments, we would, I guess, need to see standardized first before we are brave enough to do that. Okay, so the first question is about neighboring houses. What happens if we have two neighbors with the same system deployed? Yeah, so we considered this. Basically, we decided that it's enough to have different security keys for each house, so we avoid accidentally joining the wrong network, and we avoid sniffing accidentally some wrong traffic. But in terms of interference, so we sort of optimize for the worst case situation, and that's why we need so many slots in the schedule. But actually, in the most situations, we don't use all of the slots in the schedule, so we still have quite many unused slots. So it's quite unlikely that both houses will be using the same channel at the same time instant. So there's no real issue with interference, I believe. And the second question is about the LoRa protocol, where we're not using LoRa. It's basically because of the data rate requirements. LoRa and BIoT is not able to deliver that.
Any other questions? If not, thank you very much, Dr. Attis. And this will be the end of the session. Thank you, everyone. Have a good day. Bye-bye.
Test, test. Test, test, test. Is that?